tangent vectors and normal vectors. First, we consider tangent vectors. A tangent vector is said to be a vector that exists on a smooth curve. Let capital C represent the smooth curve. Represented by R, a position vector on some open interval I. The unit tangent vector, capital T, a function of time, is said to be the derivative of the position vector divided by its norm, where the derivative of R of T is not the zero vector. Graphically, if we have a curve flowing in some type of orientation, the tangent at a particular point here at 1, at x equal to 1, or little t rather equal to 1, that the tangent is said to be a line that touches the curve, but the tangent flows in the direction of the orientation of the graph. With the tangent vector, we want to talk about the principal unit normal vector. Let C be a smooth curve represented by a position vector R on some open interval I. If the derivative of the tangent vector is not zero for all values of t, then the principal unit normal vector is given with this particular ratio. Capital N of t is equal to the derivative of t divided by the norm of t prime. With the normal vector and the tangent vector, we want to try to make the connection between acceleration in these particular vectors. We have two vectors associated with their respective components. So with the tangent vector, there is said to be its component. The word component is just another word for coefficient. So the coefficient for this tangent vector is said to be the tangential component of acceleration. And then the component or the coefficient for the normal vector is a sub n, or the normal component due to acceleration. We say that the acceleration, this is the acceleration vector theorem, that the acceleration lies within the plane determined by the tangent and the normal vectors. Now graphically you can see that. And so here you have acceleration, the acceleration vector, and that this acceleration vector is determined by the tangent vector and the so-called normal vector. The tangent and the normal ideally are perpendicular. Now, two things I want to note here about the tangent vector and the normal vector. That the tangent vector will flow in the direction always of the movement of the particle along the curve. The normal vector will always face in the direction of concavity. So if we have concavity like so, then the normal vector is in that particular direction. The so-called measurement of the tangent vector is attributed to a sub t. So this dot product of the acceleration with the tangent vector gives us the tangential component of acceleration. And the dot product of a and n gives us the normal component of acceleration. So the measurement, so the so-called measurement with respect to acceleration of the tangent vector is said to be a sub t. And the measurement of the normal vector with respect to acceleration is said to be a sub n. How do we compute the tangential and normal components of acceleration? By the way, A sub n is what we consider centripetal force, or the centripetal component of acceleration. So A sub A sub t is simply the dot product of A and the tangent vector. Some who may not want to calculate the tangent vector, if you find the first derivative of r, so take the dot product of the velocity in acceleration vectors divided by the norm of velocity, and you get the tangential component of acceleration. A sub n, a dot product of the acceleration and the normal vector. And I think when you consider that, again, if we look at what's happening with the graph, again, this is A sub t, and this is A sub n. Now, next we want to take some problems where we want to find the tangent vector, the normal vector, and then from there, thirdly, we will calculate the tangential component of acceleration and the normal component of acceleration.